Download this code from codegive.com, link in the description below. Why array indices start at 0, a deep dive. The seemingly arbitrary decision of starting array indices at 0 in many programming languages, including C, C++, Java, Python, JavaScript, and others, is a source of confusion for many beginners. It might seem more natural to start counting at 1, as we do in everyday life. However, there's a very specific and logical reason behind this convention, rooted in memory addressing and pointer arithmetic. This tutorial will explain the why in detail, going from conceptual explanations to practical code examples in C and Python. Understanding the core concept, memory addressing and offsets. At the lowest level, arrays are stored as contiguous blocks of memory. Each element of the array occupies a certain amount of space, determined by its data type. Example: an integer takes up more space than a character. The key to understanding zero-based indexing lies in how the computer accesses elements within this block of memory. Instead of directly storing the memory address of every element in an array, a more efficient approach is used. One base address *, the starting memory address of the entire array, is stored. This is often called the base address or starting address. 2 element size *, the size, in bytes, of each element in the array is known based on the data type of the array. 3 offset calculation * to access a specific element, the computer calculates an offset from the base address. The offset represents the distance, in bytes, from the base address to the desired element. The mathematics of array access. The address of an element at index I can be calculated using this formula. Address of element I equals base address plus I * element size. Let's break down why this formula is so important. Base address * where the array begins in memory. This is the reference point. I * the index of the element you want to access. Element size * the number of bytes each element occupies in memory, example 4 bytes for an integer, 1 byte for a character, etc. The zero-based advantage. Now, consider what happens when we want to access the first element of the array. If we started indexing at 1, the formula would become address of element 1 equals base address plus 1 * element size. This would calculate the address of the second element, not the first. To access the first element, you'd need a clumsy adjustment or a different formula altogether. However, with zero-based indexing, when I is 0, address of element 0 equals base address plus 0 * element size equals base address. This beautifully simplifies the equation. The address of the element at index 0 is simply the base address of the array. The offset from the beginning of the array to the first element is 0. In essence, the index directly represents the offset. Code examples. Let's illustrate this with C, which provides explicit control over memory and pointers, making the underlying mechanics much clearer. Then, we'll look at Python, which handles memory management behind the scenes, but the principles remain the same. See example *. Explanation of the C code *. 1 array declaration * int numbers 5 equals 10, 20, 30, 40, 50, creates an array of 5 integers. 2 base address * int * base address equals numbers, assigns the base address of the array to a pointer variable. In C, the array name, example numbers, often decays into a pointer to its first element. 3 element size * int element size equals size of, int, determines the size, in bytes, of each integer element. 4 array indexing * numbers I is the standard way to access elements using array indexing. 5-pointer arithmetic ***, base address plus I, difference a pointer after adding an offset. This is the key demonstration. Base address plus I calculates the address of the ith element, and the asterisk operator retrieves the value stored at that address. This directly reflects the memory addressing formula in C. Pointer arithmetic automatically takes the element size into account. If base address points to an int, adding 1 to it advances the pointer by size of int bytes. 6 address printing *printf, address of numbers 0, %p\n, void asterisk, and numbers 0, prints the actual memory address of the element numbers 0. You'll see that the addresses of consecutive elements are element size, usually 4 bytes apart. The void cast is necessary because %p expects a void. Key takeaway from the C code ***. The C code clearly shows that numbers I is syntactic sugar for ***, numbers plus I. The index I is directly used as an offset from the base address. Starting at 0 means that numbers 0 is simply **, numbers plus 0, which differentiates the base address directly, providing the value of the first element. Python example ***. Python's memory management is abstracted away from the programmer, but the underlying principle remains the same. Explanation of the Python code ***. 1 list creation *my_list equals 10, 20, 30, 40, 50 creates a Python list. 2 list indexing *my_list I is the standard way to access elements in a Python list. 3 underlying implementation *, while you can't directly access memory addresses in Python as you can in C, the core concept of offset still applies. When you use my_list I, Python internally calculates the memory address of the element by adding an offset, based on I and the element size, to the base address of the list. 4 sys.gets as of, my_list 0, gets the size of each element in bytes. 5 sys.gets as of, my_list, gets the size of the list object. Why is 0-based indexing better than 1-based indexing, or other choices? 1 Simplicity and efficiency as we've seen, 0-based indexing simplifies the address calculation formula, making it more efficient. There's no need to subtract 1 from the index before calculating the offset. 2 Pointer arithmetic alignment ** It aligns well with pointer arithmetic, which is a fundamental concept in lower-level programming languages like C and C++. The index naturally corresponds to the offset from the base address. 3 Empty ranges ** 0-based indexing makes it easier to represent empty ranges. For example, in a slice arr start end, if start equals end, the slice is empty. This is more intuitive than having to adjust the indices. For historical reasons ** Fortran, an early programming language, used 1-based indexing. However, languages like C, which were designed to be closer to the hardware, favored 0-based indexing for its efficiency and alignment with memory addressing. The influence of C on subsequent languages is a major factor in its prevalence. Why isn't everyone using 0-based indexing? While 0-based indexing is the dominant convention, some languages, like Lua, R, and MATLAB, use 1-based indexing. The primary reason is often user-friendliness, especially in domains where people are used to counting from 1, example mathematical notation. In these languages, the emphasis is more on ease of use than raw performance. Conclusion: the decision to start array indices at 0 is not arbitrary. It's a deliberate choice rooted in the underlying memory model of computers and the efficiency of address calculations. While it might initially seem confusing, understanding the concept of offsets and base addresses clarifies why zero-based indexing is the most logical and efficient approach for many programming languages. Although some languages prioritize user experience over strict adherence to low-level memory concepts, the advantages of zero-based indexing in terms of efficiency and alignment with pointer arithmetic have made it the dominant convention in the programming world.